we are going to derive the Cauchy's integral formula, and the statement is, if fz is analytic within an enclosed curve C and A is any point within C, then f of A is equal to 1 divided by 2 pi iota the integral of fz divided by z minus A dz over the closed curve C. This sign represents the closed curve. And in general, if we take the nth derivative of f of A, then that will be equal to n factorial divided by 2 pi iota the integral of fz divided by z minus a the power n plus 1 over the closed curve C. It is very easy to learn. If I am having n over here, then the factorial will be n factorial, and here you have to raise the power n plus 1, right, for if I am having the nth derivative. So let's start with the proof, but before that, here are some remarks that are very important, which are used in the proof. These remarks are based on the Cauchy's theorem. The first corollary is, if fz is analytic in a region R and P and Q are 2 points in R, these are the 2 points in R, then the integral of fz is independent of the path joining P and Q and lying entirely in R, which means if you take the integration of fz dz for the path PBQ, right, then this integral is equal to the integral of fz dz along the path PAQ, right. These two integrals are same. That means the integral is independent of these paths, right? Okay. Next, if fz is analytic in the region bounded by the two simple closed curves C and C1, if fz is analytic in the region bounded by these two curves, if fz is analytic between this region, then the integral of fz dz along the curve C is equal to the integral of fz dz along the curve C1. This is the curve C1, the inner curve is C1, so the integral along these two curves are equal, right? So now let's move on to the proof, because we need to show that f of A is equal to 1 divided by 2 pi iota integral of fz divided by z minus a. So let's take this function first. So we consider the function fz divided by z minus a, which is analytic at every point within C except at z equal to a. Why? Because if I take z equal to a, I am getting the denominator to be equal to 0, then this function is not defined. So except z equal to a, fz is analytic everywhere within this curve C, right? Let's take the circle C1 entirely inside C, and let center of C1 be A and the radius of C1 be, let's say, rho. Let the radius be rho and let this be the point Z. So because if this function is analytic within the circle C, then this function is also analytic between C and C1. The region between C and C1. So we write, thus fz by z minus a is analytic between C and C1 because it is completely analytic within C, right, except at z equal to a. So therefore by Cauchy's theorem we write, the integral of fz divided by z minus a dz over the curve C, the closed curve C, is equal to the integral of fz divided by z minus a over the curve C1, right? These two integrals are equal from the remark 2. And now the equation of circle C1 would be, the circle C1 is mod z minus a equal to rho. It is having the center A and the radius rho for the circle C1. So we write the equation of the circle to be mod of z minus a equal to rho, right? And in polar coordinates, and in polar form we write from here z minus a equal to rho e the power iota theta in polar format. So from here we get z to be equal to a plus rho e the power iota theta. And now we are going to substitute the value of z over here. So if z is equal to a plus rho e the power iota theta, then dz will be equal to, because a is constant, so this is rho e the power iota theta into iota d theta. So the integral of fz by z minus a over c1 will be equal to, it is the integral of f, I'm writing the value of z to be a plus rho e the power iota theta divided by z minus a. If I take a to the other side, I get this to be rho e the power iota theta, right? And dz will be this, that is iota rho e the power iota theta d theta, and the limits will be from 0 to 2 pi for the circle, right? So cancelling these two, and we get this to be equal to iota. I'm taking iota outside the integral, and it is f of a plus rho e the power iota theta d theta. And from here, if I mark this as 1, because the integral over c1 is equal to the integral over c, right? So I can also write the value for this integral to be also equal to the integral of fz divided by z minus a dz over the closed curve C. So its value is also equal to this. Now in the limiting form, as the circle C1 shrinks to the point A, this is the circle C1, this is the center A. If this circle shrinks to the point A, which means here the radius is tending to 0. When the circle is shrinked to a point A, the radius is tending to 0. So for this limiting form, we are taking this rho to be tending to 0 in the limiting form, right? So let's write this. In the limiting form, as the circle C1 shrinks to a point A, that is rho tends to 0, then from 2 we get this to be equal to, okay, let me mark this as 2. So in the limiting form, as the circle C1 shrinks to a point A, that is rho tending to 0, then from 2 we have the value for this integral to be, I'm having here iota, the integration from 0 to 2 pi f of a plus rho e the power iota theta, because rho is tending to 0, so we are having only a. So this is f of a d theta, right? And f of a is constant. Taking this outside of this integral, f of a into iota, and integrating 1 with respect to theta, so that gives theta, limits from 0 to 2 pi. When putting the upper limit, we get this to be 2 pi minus the lower limit 0, that is we are having this value to be 2 pi iota into fa, right? So this is 2 pi iota into f of a. If I take this 2 pi iota on the other side in the denominator, what I am getting, our formula to be f of a is equal to 1 divided by 2 pi iota integration of fz divided by z minus a dz. And now for the higher derivatives. 1 divided by 2 pi iota integral of f of z divided by z minus a dz. Right? This is our Cauchy's first integral formula. Let's differentiate both the sides partially with respect to a. So when differentiating both the sides with respect to a, we get f dash a to be equal to 1 divided by 2 pi iota, the integral of f of z, and now differentiating 1 divided by z minus a. That means we need to differentiate z minus a the power minus 1. So when differentiating this with respect to a, we get minus z minus a the power minus 2 into differentiating also the terms inside the bracket with respect to a, that is minus 1. So we are getting this to be 1 divided by 2 pi iota the integral of f of z divided by z minus a whole square dz. We have to write dz also. For the second derivative we have to differentiate both the sides of this equation, right? So when derivating with respect to a, we get on the left hand side f double derivative of a, and on the right hand side we get, when differentiating this, we get 1 divided by z minus a cube and also 2 multiplied with this, and we can write this 2 as 2 factorial. 2 factorial is 2, right? So when differentiating both the sides we get this to be 2 factorial divided by 2 pi iota the integral of f of z divided by z minus a whole cube dz. Please remember, if you are taking the second derivative, increase the power by 1. And if I am having the second derivative, write here 2 factorial. For the third derivative, similarly we can write here 3 factorial divided by 2 pi iota the integral of f of z divided by, we need to increase the power by 1, that is 3 plus 1, that is 4. So in general we write this further as, for the nth derivative the formula becomes n factorial divided by 2 pi iota the integral of f of z divided by z minus a the power n plus 1. This formula is very easy to learn. So this is how we have proved the Cauchy's integral formula. Okay, thank you.